Welcome back to Physics 192. I'm Gerard Blanchard. We've been talking about optics, or the propagation of light waves. Last time, we showed two things that we're going to refer back to this time. One is that when a light ray passes through a plate of glass, where both sides of the glass is parallel, the light ray emerged from the glass moving in the direction that it was moving originally. However, if the two sides of the plate of glass are not parallel, such as if we have a prism, then the light is deflected overall, meaning that it comes out of the prism traveling in a different direction than it did originally, and specifically the light was bent towards the thicker end of the prism. We're going to use that idea to study lenses. Lenses can be categorized into two categories, converging and diverging lenses. As we said, light bends towards the wider end of a prism. A lens that is thicker in the middle is a converging lens, and you can see an example of that in the diagram on your right. If the lens is thicker in the middle, then light that passes through the lens will be bent towards the middle, and it will converge on a point that we call the focal point. If the lens is thicker on the edge and thinner in the middle, then the light will diverge from the middle, and we have a diverging lens. In that case, the light appears to be diverging from a virtual focal point. The light never actually converges on the virtual focal point, which is why we call it a virtual focal point. And so we can quantify the effect of a lens with its focal length. The focal length is the distance that the focal point is from the lens. For a converging lens, the focal length is positive. For a diverging lens with a virtual focal point, the focal length f is negative. So focal length is measured in units of length, or meters. For lenses that are spherical lenses, we can actually calculate the focal length of the lens. A spherical lens is a lens whose surface is an arc of a circle, or in 3 dimensions, part of the surface of a sphere. The important measure is the radius of the circles that make up the surfaces of the lens. The radius of curvature is positive for a convex surface. That means a surface that bulges out. And the radius of curvature is negative for a concave surface, that is one that caves in. And in this diagram, you can see several examples. From left to right, we have a biconvex lens where both of the surfaces bulge out. So both of those surfaces would have a radius of curvature that is positive. In the next lens from the left, we have a plano-convex lens, meaning that we have a convex side on one side and a plane on the other. For a plane, or a flat surface, the radius of curvature is infinite. The next two lenses have a shape of a meniscus, meaning that they are convex on one side and concave on the other. The meniscus on the left, the third lens, is a positive meniscus, meaning that it's thicker in the middle than on the edge. And the meniscus on the right, or the fourth lens from the left, is a negative meniscus, meaning that it is thinner in the middle than at the edges. So the positive meniscus is overall a converging lens, and the negative meniscus is overall a diverging lens. The fifth lens is a plano-concave lens. It is flat on one side and concave on the other. And then finally, we have a biconcave lens. So both sides would have radii of curvature that are negative. Now, for all of these lenses, we can calculate the focal length using this equation. 1 divided by the focal length is equal to the index of refraction of the glass that makes up the lens times 1 divided by R1 plus 1 divided by R2, where R1 is the radius of curvature of one side and R2 is the radius of curvature of the other. And remember that R is positive for a convex side and negative for a concave side, and R is infinite for a flat surface. Now, one thing that's both interesting and practical is that we can actually make a lens much thinner by cutting away flat pieces of glass and keeping just the curved sides. This is referred to as a Fresnel lens or Fresnel lens. And the reason why we can do that is that all of the refraction happens at the surface of the glass. And so we can cut out flat planes of glass. Flat planes of glass don't deflect the ray. All of the deflection goes on at the surface. So take a look at this plano convex lens, and we can cut it up and we can take out flat pieces of glass, keep only the curved surface, and actually make a much thinner lens that is a converging Fresnel lens, as you can see in the third diagram. Let me demonstrate that for you. This is a conventional glass lens. It is a converging lens. It is thicker in the middle than it is at the edges. I don't know if you can actually see that, but it does have the effect of magnifying an object. And you can see, as you can see from that penny, we can magnify the penny. Here I have a Fresnel lens. It's actually very flat, but it is also a converging lens, and it has the same effect as the traditional glass lens. So these two lenses are optically equivalent. They both will magnify by the same amount, even though this lens is actually flat. The way that that happens is that there are ridges on this glass that look like what we saw in the diagram. We can also make a diverging Fresnel lens in the same way. Here you see an image of a diverging Fresnel lens, and you can see the difference between the converging and the diverging lens. With the diverging lens, all of the surfaces slope towards the middle of the lens, whereas in the converging lens, all of the surfaces slope away from the middle. Now, how are we going to use this? We're going to use our lenses to form images of objects. When you look at an object in a mirror or through a lens, you're actually looking at an image of that object. This diagram shows you a camera making an image of a flower on a piece of film. Let me do a demonstration for you. Here I have a lantern, and on the front of the lantern I have placed a slide of an astronaut in front of the Earth. As you can see, the slide has the astronaut upside down. So right now the astronaut is head down. That's going to be significant in a moment. So the astronaut is our object that we're going to form an image of. So the object is right here. I'm going to take my lens and I'm going to make an image of the object on a screen. So we're going to capture the image of the object on a screen. So I have the astronaut. Our object is right here. Now first, you'll notice that even though we have that picture of the astronaut, when the light shines on the screen, we don't see the astronaut. All we see is kind of a blue and white blur. I can move this back and forth as much as I want, and even though the light is shining through the slide of the astronaut, we don't see a picture of the astronaut. We don't get an image of the astronaut. However, if I bring my lens in, now I can actually form an image of the astronaut, and there we see him. Note one thing, the astronaut is now right side up. So we've inverted the image relative to the object. He was head down to begin with, he's head up now, so we have inverted him. I can change the, well, actually first, let me show what happens if I move the paper away from this distance. There's only one distance at which the astronaut is in focus, given that I'm holding the lens still. So if I hold the lens still, then there's only one distance at which the astronaut is in focus, and so the distance from the lens to the screen is called the image distance, while the distance of the lens to the object is called the object distance. Now, if I move the paper away, I get a blurry astronaut. I can get him back into focus. I can get the image to occur at that distance by changing the object distance, by moving the lens. So I've changed the image distance, and I've changed the image distance by changing the object distance. If I want to bring the image in, I once again have to move the lens. So there we have him in focus again. So now notice one thing. Notice that the size of the image also changes. So when I change the distance of the object from the lens, when I change the object distance, I change the image distance, and I also change the size of the image. Let's see if I can get him. There's going to be a smallest distance at which I can form an image, and I think I'm getting close. So there's a small image right there. If I move the paper back, bring it back into focus, now I have a larger image. So the image distance is related to the object distance. Now that's using our traditional glass lens. I can do the same thing using our Fresnel lens, our credit card lens. It also can form an image because it is functionally the same as our traditional glass lens. So our object is right here. Our image is forming over here. And this is a real image, meaning that we can actually capture the image on a piece of paper. So when you look at an object in a mirror or through a lens, you're actually looking at the image of that object. Now, let's learn how to find where the image of an object is formed. In this diagram, we have a converging lens, and you know that it's going to be a converging lens because it's thicker in the middle than at the edges, so it's going to cause the light to bend towards the middle or converge. We have an object, which is a pencil, standing on its tip with its eraser in the air. Now, we have to assume that there's some light source shining on the pencil, so that when the light shines on the eraser, we have diffuse reflection, and the light from the eraser goes out in all different directions, as represented by ray 1, ray 2, and ray 3. We can use these rays to find where the image is formed. We really only need ray 1 and ray 2. What does ray 1 do? Ray 1 goes out from the eraser parallel to the axis or the center line of the lens, and when it encounters the lens, it bends towards the focal point, the principal focal point of the lens. So you can see ray 1 going out parallel, bending towards the axis, and encountering the axis at the distance f, the focal length of the lens. Ray 2, the second ray of light, goes from the eraser to the middle of the lens. And when a ray of light passes through the middle of the lens, that's where the lens is flat. So the ray 2 isn't deflected at all. So ray 2 goes straight through the lens. And where ray 1 and ray 2 meet up, that's also where all the other rays of light will meet up. So all of the light from the eraser will meet up at the same position, the position where ray 1 and ray 2 meet. You can see that ray 3 also meets at the same position. So all of the light from the eraser, from the actual object, the eraser, meets up at the image of the eraser. So if we were to put a screen at the point that says image, we would actually see an image of the pencil. So to find the image, you use ray 1 and ray 2. Ray 1 is parallel to the axis or the center line of the lens, and when it encounters the lens, it bends towards the focal point. Ray 2 goes straight through, because it goes through the ray 2 goes straight through the center of the lens and is not bent at all. And where those two rays meet, every other ray of light will meet. And that is where the image is formed. So we can use a ray diagram to find where the image of an object is formed. We can also calculate where the image is formed. We will represent the object distance with the letter P. So P is the object distance. It is positive in front of the lens, where the front is defined by where the object is. The image distance, or the distance of the image from the lens, will represent with Q. So Q is the image distance, and for a lens, Q is positive behind the lens, or in the direction where the light goes. F is the focal length of the lens, and it is positive for converging lenses and negative for diverging lenses. Then we have an equation. 1 divided by F is equal to 1 divided by P plus 1 divided by Q. So that is our equation to find the image distance from the object distance. 1 over F is equal to 1 over P plus 1 over Q. So we use this equation to find the location of the image. We can also calculate the size of the image. If we let h represent the object height, or the height of the object, and let h prime represent the image height, or the height of the image that is formed, then m, a lowercase m is called the magnification, where m is defined to be h prime divided by h. So that is a definition. M is defined to be h prime over h. And we have an equation for the magnification. The magnification is equal to minus q divided by p. Or in other words, h prime divided by h is equal to minus q divided by p. And we can use these two equations. 1 over f is equal to 1 over q plus 1 over p, and h prime over h is equal to minus q over p to calculate everything we need to know about the image of an object. Now, once we calculate what we need to know about the image of an object, we can use that to describe the image. An image can either be upright or inverted. If the magnification is greater than 0, then we have an upright image. When we looked at the penny before, the lens actually didn't invert the penny. We saw Lincoln with his head in the same direction, both on the penny itself and when we looked through the lens. So when we were looking through the lens at the penny before, that was an upright image. When we looked at the astronaut, however, that was an inverted image. In other words, the astronaut was head down to begin with and head up afterwards. So the image was inverted relative to the object. The image can also be enlarged or reduced. We can figure that out from the absolute value of m. If the absolute value of m is greater than 1, then we have an enlarged image, meaning that the image is bigger than the object. And if the absolute value of m is less than 1, then we have a reduced image, meaning that the image is smaller than the object. An image can also be real or virtual. A real image is an image where we can actually put a screen at that location and project the image onto a screen. A virtual image cannot be projected, and we'll see both of those later. If q, the image distance, is greater than 0, then we have a real image. Let's work an example. For a converging lens with a focal length of 3.5 centimeters, find the object distance that will result in an inverted image with an image distance of 5 centimeters. Use a ray diagram to verify your calculations. Is the image real or virtual, and what is the magnification? Go ahead and draw a diagram of this situation and list all of your knowns and unknowns and start working, please. Okay, here is our axis and our converging lens. It's a converging lens, so it's thicker in the middle than on the sides. The object is over here somewhere. The image is on this side. The focal length, f, is equal to 3.5 centimeters, or f is equal to 0.035 meters. We're told that the image is 5 centimeters from the lens, so q is equal to 5 centimeters, or q is equal to 0.05. So that is our image distance. The object distance is unknown, and that's what we're looking for. We're looking for the object distance. We can calculate that using 1 over f is equal to 1 over p plus 1 over q, or 1 over 0.035 is equal to 1 over p plus 1 over 0.05. I'm going to subtract 1 over 0.05 from both sides, and I have 1 over 0.035 minus 1 over 0.05 is equal to 1 over p. Now let's calculate that. Now be sure to do it in exactly this order. 1 divided by 0.035 minus 1 divided by 0.05, and we might even put parentheses around this to help you remember the order in which to do this. So 1 divided by 0.035 minus 1 divided by 0.05. That gives us 8.57 is equal to 1 over p, or p is equal to 1 over 8.57, which is 1 divided by 8.57. P is 0.117 meters, or P is equal to 11.7 centimeters. So we're predicting we're calculating an object distance of 11.7 centimeters. So that would be somewhere over here. This is 5 centimeters, so that's 5 and another 5, so somewhere over here is our object. And I'll let this be my object. So P is equal to 11.7 centimeters. That's this distance right here. Okay, let's do a ray diagram to check and see. Okay, my first line goes parallel to the axis and then goes to the focal point. So that was ray 1. Ray 2 goes straight to the center of the lens and carries on straight. So ray 1 is parallel to the axis and then goes through the focal point. Ray 2 goes straight through. And you can see that they do indeed meet right about where we expected them to. So these two light rays meet up together with all of the other light rays at this real image. So the light rays really meet, so we have a real image. Also, it is inverted. Notice that the arrow is pointing up over here, but the light from the top of the arrow is above the axis over here, but it meets below the axis over here, so it's inverted. And also, this arrow looks a lot smaller than this arrow, so it is a reduced image. Let's verify this, all of this, with our calculations. Well, we've already verified that it's real. Or we were told that it's real, really, because we were told that Q is 5 centimeters. So Q is greater than 0 is consistent with a real image. So Q greater than 0 for a real image. All right. How about the magnification? The magnification is equal to H prime divided by H. The H prime divided by H is equal to minus Q over P. So the magnification is equal to minus Q divided by P. So the magnification is minus Q, which is 0.05, divided by P, which is 0.117 in meters. We have meters in both cases. So the magnification is equal to negative 0.05 divided by 0.117. Magnification is negative 0.427. And I'll just point out, I'm still going to stick to my convention of using basic metric units for my quantities when I do calculations, so that we know what units we have. We wind up with a magnification of 0.427. The magnification is negative, which is consistent with inverted. So inverted is consistent with m less than 0. The absolute value of m is equal to 0.427, and the absolute value of m is less than 1. So that is consistent with a reduced image. Absolute value of m less than 1 is consistent with reduced. So both our diagram and our calculations tell us that we have a real, inverted, and reduced image. So that is how we find an image with a converging lens. We can do something very similar with a diverging lens. Here we have a pencil and a diverging lens. Something is shining light on the pencil, and we have diffuse reflection, and the light goes off in all directions. We have 3 light rays shown. Once again, we only really need 2 light rays, and we're going to stick to ray 1 and ray 2, which are the counterparts of the 2 light rays that we used for a converging lens. The diverging lens has a virtual focal point, or a negative focal point, or a focal point that is on the same side of the lens as the object, and that's marked the principal focal point in the diagram. Ray 1 is the ray that goes from the eraser parallel to the axis. When it reaches the diverging lens, it bends towards the thicker end, which is the edge, and so it bends up in this case. And what direction does it bend in? It bends directly away from the virtual focal point. Remember, for a converging lens, ray 1 bent towards the real focal point. For a diverging lens, ray 1 bends directly away from the virtual focal point. Ray 2 goes from the eraser through the middle of the lens, and it's not deflected at all. It goes straight through. So ray 2 is not deflected, and ray 1 and ray 2, once they reach the lens, they diverge. They never meet up. So where is the image? Well, we don't have a real image. We have a virtual image. Ray 1 and ray 2 never meet, but if we trace them back, they seem to have met at the virtual image. And you can see it, that little tiny pencil in the diagram is where ray 1 and ray 2 would meet if we were to trace them back. So that is what a virtual image is. The light never actually converges at a virtual image, although it appears to have converged at the virtual image. So once again, for a diverging lens, ray 1 is parallel to the axis, bends directly away from the virtual focal point. Ray 2 goes to the middle and goes straight. And then we trace the rays back to find the virtual image. Let's work an exercise. An object of height 3 centimeters is placed 12 centimeters from a diverging lens of focal length -12 centimeters. Calculate and draw a ray diagram to find the height and position of the image. Go ahead, draw your diagram, list your knowns and unknowns, and get started calculating, please. Okay, here is our axis. Here is our diverging lens, thicker on the edge than in the middle. We'll place our object 12 centimeters from the lens. So P is equal to 12 centimeters, which is equal to 0.12 meters. And the focal length is -12 centimeters as well, which means that the focal point is not over here, but it is a virtual focal point back here, and they happen to be at the same point. F is equal to -12 centimeters, or F is equal to -0.12 meters. So that's our focal length. Let's go ahead and draw our ray diagram just to see what we expect here. Okay, ray 1 goes parallel to the axis, goes through the lens, and bends directly away from the virtual focal point. Okay, so what I did is I traced back to the focal point and then carried the ray out. So that's ray 1. Ray 2 goes directly to the lens and keeps on going. So they never meet, but if we trace back ray 1 and trace back ray 2, it appears that they came from here. So this is our object distance. This distance right here is Q, and we don't know what that is, but we'll figure it out. We're also told that the height, H, is equal to 3 centimeters, or height is equal to 0.03 meters. And we don't know what H prime is, but we're expecting H prime to be smaller than H because in our diagram it appears smaller. We're expecting Q to be negative because it is a virtual image. And we're expecting the magnification to be positive because the image is upright. Okay, let's do our calculations. 1 over f is equal to 1 over p plus 1 over q. 1 over negative 0.12 is equal to 1 over 0.12 plus 1 over q. So 1 over negative 0.12 minus 1 over 0.12, and I'll put parentheses to help you with your calculations, is equal to 1 over q. What does that equal to? 1 divided by negative 0.12 minus 1 divided by 0.12 is equal to 16.7. I'm sorry, negative 16.7. Negative 16.7 is 1 over q. So q is equal to 1 over negative 16.7. 1 divided by negative 16.7 is negative 0.060. No, I'm sorry, 599. 0.0599 is equal to q, and that's in meters. So 5.99 centimeters is equal to q. So that's exactly what we were expecting. I'm sorry, and I lost my negative sign there, negative. So q is negative 5.99 centimeters. So that means that q is negative, meaning that it is to the, it is in front of the lens, meaning it is a virtual image. So q is less than 0. It tells us we have a virtual image, just as we expected. Let's calculate the magnification. The magnification is h prime over h, where h prime over h is equal to minus q over p. So h prime is equal to minus q over p times h, or h prime is equal to minus negative 0.0599 divided by 0.12 times h, which is 0.03, or h prime is equal to negative 0.0599 divided by 0.12 times 0.03. That tells us that the height is 0.015 meters, or 1.5 centimeters. And that's one thing we were asked for, is what is the image height? The image height is 1.5 centimeters. But let's also check the magnification. Magnification is h prime over h. So the magnification is 0.0150 divided by 0.03. 0.0150 divided by 0.03. So the magnification is 0.1, scratch that. The magnification is 0.5. Scratch this out. Magnification is 0.5, 1/2. So the absolute value of m is less than 1, which tells us that we have a reduced image, but m is greater than 0, which tells us that we have an upright image. So we have a virtual reduced upright image according to our calculations, and also according to our diagram. We have a virtual image because the light rays don't actually meet here, they only appear to meet here. It's upright because it's pointing upright, and it's reduced because this arrow is smaller than that one. We'll do a lot more with optics next time. Until then, think physics.